This is a video covering the instruction set of my relay computer as it currently stands in March 2018. To get things going, I'll start off by quickly covering the computer's architecture, which will help us make sense of the upcoming instructions. If you've been following my videos and blog, you'll have seen this diagram many times, but effectively it shows the various units of the computer and how they can communicate with each other. The green blocks are items that have been constructed, whereas the blocks in red are yet to come. Starting top left, we have the general purpose registers A, B, C and D, with each register able to hold a single 8-bit value. The value in any of the 4 registers can be gated to the data bus on the left, and whilst that value is on the data bus, another register can be loaded with that value. The arrows to the left of each register show the value can go in and out of the register. Register B and C are also directly connected to the ALU as read-only inputs. The ALU can then combine those inputs in various ways, with the result then put back out to the data bus. Following an ALU operation, the special registers Z, C, Y and S are also set accordingly to the operation result. If the result is 0, register Z is set. If the most significant bit is set, also known as a sign bit, then S is set. And finally, in an arithmetic operation such as add or increment produced a carry bit, then CY is set. These ALU flags aren't really used at the moment, but will become important when I implement branching on the computer. Below the general purpose registers, there are a further 4 general purpose registers that haven't been constructed yet: M1, M2, X and Y. Like registers B and C, these all have a second specialised purpose. M1 and M2 combine to form a 16-bit M register, which can be gated to the address bus but not loaded back from it. Similarly, registers X and Y combine to form the 16-bit XY register, which can be gated and loaded from the address bus. In practice, the M register will typically be used to address locations in memory, while the XY register will be used to store return addresses when doing subroutines in code. Below those is the J1 and J2 registers, which combine to form the 16-bit J register. These can only be loaded from the data bus and are only gated to the address bus. The J register will typically be used for providing an address to jump to depending on the contents of the ALU flags. Effectively, we're talking branching here again, which is all to come in the future. Next up, we're back into green blocks, and things that actually exist in the computer today. The next 3 blocks are all registers again, but are even more specialised. Inst is the instruction register, which holds the current instruction being operated. It's loaded from the data bus, and from there is used by the decoder and controller circuitry in order to operate the various control lines at the right time according to the instruction opcode. PC is a program counter, which holds the address of the current instruction in the program, and when branching gets implemented, we'll be able to make the program counter jump to different locations in the program depending on the result of the ALU operation. Inc is the incrementer register, which takes its input from the incrementer, which takes the value on the address bus and adds 1 to it. The incrementer and associated register is mainly used to push the program counter onto the next instruction in memory, but eventually we'll be able to increment the XY register. Finally, at the bottom right is the memory unit, which, given a location from the address bus, can then load or save a value from or to the data bus. Okay then, so that's about as brief a summary as I can give really, but if you want more information, then my blog at relaycomputer.co.uk has plenty more details. So, with the architecture in the bag, let's move on to our first instruction, load immediate, which allows the programmer to load a sign extended 5-bit value into either register A or B. Each instruction falls into an instruction class, and for this one, it's set AB. The decoder recognises load immediate instructions as being part of this class, and that knowledge is then used to direct the controller circuitry. For each instruction, I'll introduce an assembly mnemonic, which makes it easier for the programmer to memorise when creating programs. For load immediate, the mnemonic is LDI. The instruction takes 2 parameters separated by a comma, with the destination coming first, either A or B, and then the value to load coming second. Here are some example load immediate instructions. The first column shows loading a decimal value and given it's a 5-bit value, we can go anywhere from -16 up to 15. In the middle column, you can see the equivalent instructions using hexadecimal notation, with the values prefixed with a 0x. Finally, in the last column, there's a binary equivalence, with each value suffixed with a b. As a programmer, you can use any of these notations as you see fit. When programs are compiled, these assembly mnemonics are converted to the opcodes the computer requires. Here's a diagram showing how the opcode is derived. As you can see, the resulting 8-bit opcode is fine for the computer, but not particularly human readable, and that's why we create programs using these assembly mnemonics. I'll finish off by showing how the sign extension works. For a value that starts with a 0-bit, then the resulting 8-bit value is filled with zeros to the left. In this example, we've requested a value of 13, which is unaffected by the sign extending. The example on the right starts with the most significant bit set, which gets extended to the full 8-bit value, hence preserving the representation of a negative number. Interestingly here, of course, is that the number is only negative because we're perceiving it that way. As with all numbers stored in the computer, it's up to the programmer to decide if a value with the most significant bit set is negative or just a larger unsigned number. The computer itself doesn't really care either way, it's just an 8-bit value. Right, let's move on to the next instruction, which coincidentally is itself named move. This is an 8-bit move operation, which will therefore interact with the 8-bit data bus. Even though the instruction is called move, it actually copies the contents of one 8-bit register to another, and the class of this instruction is move8. The mnemonic for this instruction is MOV, which is pretty consistent with instruction sets on many other computers. It takes two parameters. First is the destination register, A, B, C or D, and the second is a source register, again A, B, C or D. It might seem odd that the destination comes before the source, as perhaps in natural speech you'd expect it to be the other way around. But again, the convention for the MOV instruction is to have it this way around. This is also then consistent with the load immediate instruction, which could be seen as moving a value V into destination D. Here's some examples of the move instruction. Copy B into A, D into C, and A into B. The last one is quite interesting, and probably not immediately obvious what it does. We're copying the value into register A from register A. Now it depends on the computer, but in the case of my relay computer, this instruction will effectively clear the value in register A, setting it to 0. Again, it's up to the programmer if they want to use this side effect, and of course there are multiple ways of loading a 0 into a register. Compiler-wise, here's how the opcode is derived from the assembly mnemonic. Next up, we have the arithmetic operations. These come under the ALU class of instructions, and as it's the ALU we're dealing with here, we'll be taking inputs from the B and C registers as the architecture diagram shows. There's 3 mnemonics in this group: add, increment and clear. Add takes the value in register B and C and places a sum onto the data bus. We can choose to either load that value into register A or D via the parameter. The parameter is optional, and if we don't specify it, the compiler will assume we want register A. This saves a few keystrokes, as more than often you'll want to use register A, which is notionally the accumulator register. By performing repeated adds, followed by copying register A into B, you can effectively perform multiplication with the value in register C. Increment takes the value in register B and adds 1 to it. Again, you can choose a destination register of either A or D, and A is assumed if the destination isn't specified. The value in register C is ignored for this operation, so it can contain any value without affecting the increment. For both the add and increment operations, the ALU will set the carry bit if the result overflowed, and likewise will set the 0 and sign bit as appropriate for the result. Clear is another interesting one, which performs an ALU no-op. That is, it will go through all the motions of a normal ALU operation, such as loading the destination register and setting the ALU flags, but the result is always 0. Effectively, this clears a destination register and sets it to 0. So this is the second way of zeroing a register, but note it can only be done on register A or D, as that's the only registers the ALU can reach. Now the reason the ALU can't load B and C is that will create a feedback loop in the circuitry of the computer, which would damage the relays as they would oscillate on and off at very high speed. Here's some examples of the add and clear instructions, with the first column implicitly loading register A, the middle column explicitly loading register A, and the final column loading register D. Here's a truth table for the ALU add and increment operations. I is the arithmetic unit carry in, and O is the carry out. R is the result generated. Next, I've added an example of adding two 8-bit values together, and above, an example of adding two numbers together where the value overflows. This sets the carrier bit, which a programmer could use to branch. Taking this further, you could add larger 16-bit numbers together held in two registers by having logic handle the carrier bit and take it through to adding together the higher 8-bit values. Finally, here's an example of an increment operation. I'll show the opcode diagram in a bit, as there's more the ALU can do for us. And here that is, the logic operations. These also fall under the ALU class of instructions, and therefore are similar to the arithmetic ones we've just seen. There's 5 mnemonics in this group, all of which perform bitwise operations. That is, they operate on the values in a bit-by-bit fashion. The first 3 mnemonics are binary operations, in that they take two inputs, B and C, to produce a single result value. Here we have bitwise AND, OR, and exclusive OR. The last two are unary operations, which take a single input from register B. NOT negates each bit of the input, and ROLL takes each bit of the input and moves it one place to the left, with the leftmost bit being rotated back to the right. As before, each mnemonic takes an optional single parameter to specify the destination register A or D, with register A being assumed if no destination is specified. Here's some examples of the instructions in use with, again, destination A implicitly specified, destination A explicitly specified, and finally destination D specified. Here's the logic truth tables for the AND, OR, and exclusive OR operations. As you can see, AND sets the output to 1 only when both B and C are set to 1. OR sets the output to 1 when either B or C are set to 1. This is an inclusive OR, as you can have B or C or both. This differs to the OR we use in day-to-day speech, which is the exclusive OR. When we say you can have tea or coffee, we usually mean you can choose between tea or coffee, but you can't have both. Software developers love to answer these sort of questions with a binary response of yes, applying inclusive OR logic. People given this reply tend to receive a mug with a mixture of tea and coffee at my house. The truth tables for the unary operations look like this. NOT is quite straightforward. Shift left rotates all the bits one place to the left as though they are on a conveyor belt. This particular shift left is circular, but other computers do have a non-circular variance that lose the most significant bit. It might not be immediately obvious what the use of left shift has, but note effectively each shift multiplies a number by 2, plus it can have other uses. All of these instructions can be useful when you want to manipulate individual bits of a value. For example, you can use AND to only retain certain parts of the value, using a mask, or use OR to force certain bits on. Finally, exclusive OR can be used to toggle selected bits on and off. That's all the ALU class instructions, and so here is a diagram showing how the opcode is derived. So, that's all the classes of instructions we have for now covered: set AB, move 8, and ALU. There'll be plenty more to come in the future as the computer gains functionality, but for now, that's it. Here's a recap of the mnemonics we've covered, along with a brief description of each. And finally, a summary of what each does. All of the instructions ultimately impact a chosen destination register, with the value either coming from another register in the case of move, or from a literal value in the case of load immediate. Or in the case of the ALU instructions, it comes from an operation taking its input from register B and C, register B on its own, or no registers at all in the case of the clear ALU no-op. To program the computer, we take this list of instructions and combine them in various ways to get the computer to perform an operation of interest to us. Ultimately, we're just taking values into the registers and performing a set of operations on them to get a desired result. Here's the program I've used many times in my previous videos, which performs a simple arithmetic sequence of 2 plus 4 plus 1, producing 7, multiplying this by 3 to get 21, then subtracting 3 to finish up with 18. Effectively, it's a program to take my expensive and complicated relay computer and reduce it down to the level of a basic pocket calculator. To be fair, when I implement branching, that's when I can truly describe what I've built as a computer. Anyhow, the program breaks down like this. We load 2 into register A and 4 into register B. Because we're going to add these together, I need to copy the value in register A to register C, so that the ALU can get at it. With that done, an ALU add will put the value of 6 into register A, and it'll overwrite the 2 it originally contained. Next up, we copy the value into register B so that we can increment it via the ALU and get a value of 7 in register A. We now want to perform the multiplication, but the computer doesn't offer an instruction for that. That's fine though, as the computer is designed to be simple but at the expense of the programmer having to do a bit more work. We can achieve the same effect by repeated addition, which is after all really what multiplication is. We now have a value of 21 in register A, and so we now want to subtract 3. Again, there isn't a subtract operation, but we can achieve the same by adding a value of minus 3. Although I could just load a minus 3 up using the load immediate instruction, I'll take the slightly longer route for the purposes of demonstration. Here, I load 3 into register B, perform an ALU not to invert all bits, and place the result into register D, so it's out of the way of all the other values that we're manipulating. And then finally, increment this value back into register D. This produces a 2's complement of that value, which is a binary representation of minus 3. The 2's complement form is useful as it allows us to add negative numbers, getting a result you'd expect. If you add 2 to minus 2, you get a result of 0. And this is because the arithmetic unit doesn't even know we're using 2's complement. It just adds the numbers together as if they were normal unsigned numbers, which in this case would produce a result of 0 with the carry bit set. In our case, we just ignore the carry bit. Anyhow, the result of 18, as expected, ends up in register A, and the program is complete. So, I wanted to take a quick pause at this point to say thank you. When I first started making videos on the construction of my relay computer and started posting them up to YouTube, I was under no illusion of this being a mass media thing. It's an incredibly niche corner of a pretty niche interest area, and that's why I'm astonished and pretty humbled that there's over 130 people out there that are interested enough to click the subscribe button. And yeah, I know it's still pretty low even for a relay computer, but I'm still really pleased with it. So again, thank you to all those who have subscribed. 130 people, eh? And that got me thinking. You must be all sick of seeing me use the same program over and over again. So how about I invite you lovely subscribers to have a go yourself? It's your turn. I'll take the top 5 most interesting examples, subjectively judged by me, and create a YouTube video running them on my relay computer. Obviously, if I only get 5 programs, I'll run them all, but I'm hoping out of 130 plus people, there'll at least be some that fancy a go. So there's a few pointers. The program can be as long as you like, but please bear in mind I've got to manually key it all into the computer. You can either post your code in the comments or feel free to post a link to your favourite code snippet site. As long as I can get to it, I'll consider it. Feel free to ask questions, etc. in the comments, and I'll reply as soon as I can. And you can specifically request that the manual user input is entered into the registers before the code starts, but obviously not after it starts. So for example, you could say my program takes 2 numbers between 1 and 10 in registers A and B, which then I'll put in before running the program. Now I think the tricky part here is that there are no loops, no branching, no storage, and limited registers. So it'll be interesting to see if there's anything clever or inventive anyone comes up with. Now, it may even turn out that the computer in its current form is so restrictive that it's not even worth having a go, and I end up with no comments on the video, in which case I'll quietly and forlornly just get back to implementing branching on the computer. As always, you can find more information on how my computer works at my blog, relaycomputer.co.uk. But also I've put together a couple of additional things. At simulator.relaycomputer.co.uk, there's an Angular simulator of my computer. Now I've tried this on various browsers and computers, and if it's not working for you, then let me know in the comments and I'll see what I can do. It's worth noting that the simulator, like the relay computer itself, needs 8-bit opcodes, so if you're going to try your program out there, you'll need to compile it using the opcode diagrams I've been showing earlier. There's also editor.relaycomputer.co.uk, which uses Microsoft's Monaco code editor to give you an environment to type programs in with syntax highlighting, IntelliSense and so on. It's pretty basic and it won't save your code. You'll need to copy and paste in and out of the browser. But it's something I've quickly thrown together for you to use if you fancy. Again, any problems or thoughts, let me know in the comments. Right then, that'll do for now. I'm really looking forward to what comes in, fingers crossed and all that. And I'll leave you with this slide, which shows all the available instructions along with the architecture diagram. So feel free to pause the video at this point and if you want a screen grab or something similar. So thanks again for watching, and my next video will be an updated overview of the computer, and then after that it'll be time to start working on the next major milestone, which will be branching. And at that point, that's when the computer becomes worthy of the title. As always, please feel free to like, comment and subscribe, and I'll see you next time.